A student arranges a toy car track with a vertical loop of radius 20 centimetres as shown. A toy car of mass 150 grams is released from rest at a height of 1 metre at point X. The car rolls down the track and travels inside the loop. Assume that G is 9.8 and ignore friction. Calculate the speed of the car as it reaches the bottom of the loop, point Y. So we're starting up here from rest. We're travelling down to point Y. So how are we going to calculate speed? What are we going to use?
Kinetic energy.
Kinetic energy. Excellent. So we are converting our gravitational potential energy into kinetic energy. All right? So we need to work out, so the amount of energy this car has is not going to change. What is going to change is whether it is gravitational potential or kinetic. So at point X, what's its kinetic energy?
0.
Zero. That makes a lot of sense. So we've got no kinetic energy here. We need to work out its gravitational potential energy. So it's mgh is gravitational potential energy. So the mass of the car, 150 grams or 0.15 kilograms. Gravity is 9.8. And the height is 1 metre. So what is that? 1.47?
Yep.
Joules. Okay, so we've got our gravitational potential energy. This doesn't tell us anything yet. Okay, we haven't worked out, we need to find the speed. All we've got is the amount of energy. But if friction is taken out of it, we are going to keep this same amount of energy for the whole time. This car is not going to lose any energy. What's going to happen though is as we go from point X to point Y, it's going to pick up speed because all of this 1.47 joules is converted to kinetic energy. Okay, so at the bottom of point Y, we can say it has 0 gravitational potential because all of this has become kinetic. Okay, so at point Y, we have our kinetic energy is equal to 1.47 joules. All of that energy has become kinetic. And we have no gravitational potential. So, anyone remember the equation for kinetic energy?
Half mv squared.
Excellent. So, our kinetic energy is 1/2 mv squared. Now, we want to work out velocity. So, we might need to rearrange this. I'll go back up here. So, if we rearrange this equation, V is going to be equal to, I'll let you do the maths yourselves, but it's 2e on m square root. Okay? Have a play with this later if you're not sure how I got that, but by rearranging this equation, e equals 1/2 mv squared, you get this. V equals the square root of 2e on m. Okay, so the square root of 2, what was our energy again? 1.47. What's our mass? 0.15. Okay, someone calculate that for me, please.
4.43.
4.43, that sounds good to me. So if you put that into a calculator, you should get 4.43 meters per second. Okay, so that is our speed. All of our gravitational potential energy has been converted to kinetic energy. Once we know how much that is, once we know how much kinetic energy we have, we can work out our velocity. Okay, so that's part A done. We are traveling at 4.43 meters per second when we get to point Y. Calculate the normal reaction force from the track at point Y. Okay, now this is where we need to be a little bit careful. Remember, first of all, I'm going to put this equation up here. F net equals Fg plus Fn. So we want to work out Fn. Okay? So let's look at our car. All right, remember, first step, draw a diagram. At the bottom of the loop, okay, we are just entering our circle. All right, so we do consider the car at point Y is traveling in circular motion. So in which direction is F net?
Towards the center.
Towards the center. So if we're at point Y, in which direction? Up. All right. So our F net is up. In which direction is gravity? Down. And in which direction is our normal force? Up. The normal force opposes the force of gravity. Well, can't even necessarily say that. Our normal force, though, is the force of the track pushing it up. Okay? So the normal force in this case is the track pushing it upwards. Okay. So we want to get Fn, so we need Fnet first. So Fnet is equal to mv squared on r. Okay, remember that equation? So 0.15 multiplied by, what was our speed? 4.43.
Yes.
On a radius of 0.2. And I think that was 14.7. I did this earlier. Is that right? 14.7?
Did you find out?
0.15 times 4.43 squared divided by 0.2. Yep, 14.7. Okay, so our Fnet is 14.7 newtons. We want to find out eventually our normal force, but we need to get Fg first. Fg is equal to mg. So our m is 0.15 multiplied by 9.8, and that is 1.47 again, unless I'm mistaken. Yep. Okay, so we've got a gravitational force and we have a net force. We have everything we need to do to work out our normal force. Okay, so let's keep upwards as positive, and we should rearrange this. Let's rearrange. So Fn is going to be equal to Fnet minus Fg. Okay, all I've done is rearrange that top equation to make Fn the subject. So our net force is 14.7 minus, okay, so remember our, upwards is positive, so our net is positive. Fg is negative. Fg is in the other direction, so we have to minus the negative Fg. Okay? Downwards is negative, Fg is downwards, so Fg must be negative. So if we work this out, we get 14.7 minus negative 1.47, and we get 16.17 newtons. So our normal force is 16.17. So what this means, that is greater than our normal force would usually be. Okay, if the car was travelling on a straight track. So if you shrunk yourself right down and hopped in this car, you would feel heavier at point Y. Yep.
I just realised.
Yes.
I find that kind of sketchy because, for example, when he goes down the hill or whatever, he's not actually. He hasn't started travelling circular motion. Like, you could assume that he just goes to like a flat slope. Like, he's not actually moving within that circle. So couldn't you just assume that Fg equals Fn?
I totally agree with what you're saying.
Fg equals negative Fn, but yeah.
Yeah, I completely agree with what you're saying. And so Chris is saying that as we go from X down to Y, if we got rid of this loop, wouldn't you still be travelling at a straight line at point Y? You are correct. However, on exams, they mark you this way, which is the main thing you guys need to worry about. They consider, when you get to this point, that you are inside the circle, okay? Now, I guess it all depends on the steepness of the slope immediately before point Y as to whether you are in a circle or not. So if you consider this point, next to point Y is very close to a circle, if it was steeper, then you could say you're pretty close to circular motion. Whereas if it was much flatter leading into point Y, you wouldn't be. Okay? But I agree with what you're saying. It is very, I like your word, it's sketchy. But, in terms of the way you have to answer on exams, this way is how you have to answer on exams. Assume point Y is part of the circle. But I totally hear what you're saying. Okay. So, point Z. We want to work out the speed of the car as it reaches point Z. Okay, so we've gone from point Y up to point Z. Okay, so again, we're going to need to use energy again. So remember, our car had an EK of 1.47 joules at point Y. So as it goes up to point Z, some of that energy is going to be lost to gravitational potential. So it is going to slow down. It won't have as much kinetic energy. Okay? So what we need to do is work out how much gravitational potential it needs to gain to get up to point Z. Okay? So our gravitational potential is mgh. Now, sometimes it might be easier to think about gravitational potential like that. mg delta h, mass times gravity times the change in height. And in this case, this might be one of the good times to do it. So, from point Y to point Z, what's our change in height?
40 centimeters.
40 centimetres. Excellent. We have a radius of 20 centimetres on our circle. So to go from Y to Z, we have to increase our height by 40 centimetres. So our mass is 0.15 multiplied by 9.8 multiplied by our change in height is 40 centimetres. So 0.15 times 9.8 times 0.4. So we need 0.588 joules of gravitational potential energy to get up to point Z. So our kinetic energy at Z, I'm going to call this EKZ, is going to be equal to our kinetic energy at point Y minus the energy we've lost to get up to point Z. So we've lost 0.588 joules to get from point Y to point Z. So our kinetic energy at Z is going to be 1.47 minus that 0.588 joules, which is going to be equal to 0.882 joules. So at point Z, our cart has 0.882 joules of kinetic energy. Okay? It started with 1.47 down here, but it had to give away 0.588 to get up to Z. Okay? To raise its height. Okay, so now we have the kinetic energy at point Z, we can work out the speed at point Z. Okay, from that equation I showed you before. V is equal to the square root, of 2e on m. So, square root of 2 multiplied by our kinetic energy at that point is 0.88, 2 over 0.15. And hopefully, if we've done this correctly, this should be a little bit slower than it was. And I get 3.43 meters per second.
Yep.
Excellent. So, from memory, on the previous slide, we worked out at point Y, it was travelling at 4.43. So to get up to point Z, it slowed down to 3.43. Okay? So, there's a lot of energy stuff in this equation apart from the circular motion stuff. Okay? We will be practicing with this energy transformations again a lot this year, in fact. Okay? But what I want you to be aware of, have you heard of the term of mechanical energy? Have you heard of this? Yeah? So you know your mechanical energy is constant the whole way through. All right? So your kinetic energy plus your gravitational potential is a constant. If you can remember that, then you can always work out your transformations. All right. So the normal force acting on the car at point Z. Again, you need to be very, very careful with the directions things are happening in. So now our car's upside down. All right, always draw a diagram. So our three forces, Fnet, Fg, Fn. In which direction is Fnet acting? Down. Fnet is acting down. What about Fg? Down. What about Fn? Why? What is Fn? The force of the track pushing on the cart. So down. All of our forces are acting in the same direction here. So all of a sudden this becomes easier. Okay, everything's pushing downwards. So, let's work this out. We know, we want Fn. So let's, I'll do the full equation first. So Fnet is equal to Fg plus Fn. We rearrange this. Fn is equal to Fnet minus Fg. Okay. Our net force. Let's work this out down here. How are we going to work out our net force? How do we do it earlier? Sorry? mv squared r. Good. 0.15 multiplied by 3.43 squared on, was it? 0.2. 0.15 times 3.43 squared divided by 0.2. So I've got our net force as 8.82 newtons. All right, our Fg. Fg, that hasn't changed. That's still, I think, it was 1.47, wasn't it? 0.15 multiplied by 9.8, yeah. Is 1.47 newtons. So therefore, our normal force is 8.82 minus 1.47. And so we get 7.43. Oh, sorry, 7.35. So again, our normal force is less than it would normally be, and so you'll feel lighter at the top. Okay? There is a lot of work in a problem like this. But again, as long as you remember this, Fnet equals Fg plus Fn, and you make sure your directions are correct. Your negatives and positives are correct. As long as you do that, you should be able to work your way through.